what we had yesterday, and I have realized yesterday that most of us here are engineers. I'm the only one who's coming from chemistry background, probably. So I have tried to modify it as much as I could. I have tried to remove as much chemistry as I could so that it somehow suits everyone. My name is Hisham Lutfi, and I'm teaching currently at the University of Namibia Chemistry Department. And my topic today is going to be about production of biodiesel from algae. And we focused also on determining the optimum growth conditions for algae. Of course, it is well known to us that there is a continuous need for energy, and it is growing with years due to the increase in population and in industrialization as well. And it is also widely recognized currently that the petroleum fossil is an unsustainable energy resource due to some factors. Most important of it is that it is a depleting resource, and the other thing is that it has a huge negative impact on the environment, as we will shortly discuss. According to the Intergovernmental Panel on Climate Change based on Washington, D.C., they have concluded that most of the global warming which has taken place during the past 50 years is due to human activities. And a recent study which was done in 2010, they have concluded that 70% of the carbon dioxide produced is due to the combustion of petroleum oil. And if we can just look at that graph quickly, that is the level of carbon dioxide from the year 1000 up to the year 2000. We realized that up to 1800 the level was fine. And then in 1950s the increase has started to be sharp. And it is still continuing. And under business as usual scenarios, if we continue using petroleum oil the way we are using it, then the level of carbon dioxide is anticipated to increase, and it will be by the year 2100. It is estimated to be somewhere between 600, that is the best case scenario. It could reach 1000 ppm. Currently, it is less than 400 ppm. And if that happens, then scientists are anticipating an increase in temperature. The globe temperature is anticipated to increase between 2 and 6 degrees Celsius. If we take the best case scenario that the temperature by the year 2100 will increase only by 2 degrees Celsius, then that will lead to, in fact, a critical climate changes, and in fact dangerous changes are anticipated to take place. The studies are shown that under business as usual scenario, the sea level is anticipated to rise, ice caps are anticipated to go under huge mass loss, they will melt because of the global warming. Wildfires are going to escalate in both extent and frequency, and we are also anticipated to have huge floods in some areas and devastating droughts in other areas. And in fact, we have started to see that in some parts of the world. That is in Africa, severe droughts. In some areas of the world, huge floods. In fact, when I have seen that photo for the first time, I thought that is a rescue operation in one of the seas. But in fact, that is one of the cities in Bangladesh which has gone under huge flood. So that is one of the streets in a country. We are losing ice at much more frequency than it was used to be. Wildfires are escalating and the extent is increasing, and that is all due to global warming, which is carbon dioxide is responsible for 73% of it. In addition to that, studies are showing that if governments continue with their developmental plans the way they are now, then by the year 2030 we will need 60% more energy than what we use currently. And the International Energy Agency in 2007 has sent a signal, a warning signal. In fact, they said that if we continue with the consumption, then the fossil oil is going to be exhausted in less than 45 years. What could be the solution then? We are faced with many challenges. Fossil oil is going to be exhausted. It has a huge impact on the environment. It is the main reason, the combustion of fossil fuel is the main reason for global warming. In addition to that, political instability is escalating the price of the fossil oil. Some few decades back, it was less than $20 per barrel. Currently, it is 125. Economists are estimating that if something goes wrong in the Middle East region, it could quickly reach $250 per barrel. Then renewable energy might be the solution. And in fact, in the last 20 years, production of energy from renewable resources, especially biofuels, has taken much of the attention of scientists due to what we have just mentioned. Why biofuel and why biodiesel? Well, just briefly, biodiesel is non-toxic and it is biodegradable. And we will discuss in a bit more detail the advantages of biodiesel at a later stage. Algae, in fact, was reported to be one of the best sources for biodiesel. We are familiar with biodiesel produced from corn or from soybean or from sunflower, but algae is, in fact, one of the best sources which could be used to produce biodiesel. And the best algae for producing biodiesel is microalgae. We have microalgae and we have macroalgae. Macroalgae is like seaweeds, but microalgae, the one-cell algae, that is the best producers for biodiesel, and we will list the reasons for that. Algae is reported to contain anything between 2 and 40% of its dry mass fat, oil or fat. But in fact, very recently there are some types of algae which can accumulate up to 70% fat of their total mass. The per unit yield of oil from algae is estimated to be something close to 19,000 to 76,000 liters per acre per year. And this is 7 to 23 times greater than the best. Then the next best crop, which is palm oil. Palm oil produces around 2,400 liters per acre per year. In addition, when we produce algae, when we produce biodiesel from algae, then the question, food or fuel, is not raised. Because when we produce biodiesel from corn or from soybean or from sunflower, then we are always faced with that question. Do we use them to eat? Especially there are some regions in the world where there is a huge starvation, there is hunger, or do we use them to produce biodiesel? Which should be our first priority? to use food to produce biodiesel or to use food to feed the hunger. Just a few advantages of producing biodiesel from microalgae over than producing it from crops is that microalgae has a rapid growth rate. In fact, their lifespan is ranging from 1 to 10 days, but there are some types of microalgae which can be harvested every day. So we can harvest algae every day if we are growing them. They have, of course, higher per unit area yield, 7 to 30 times higher than crops. And just that is a study just to show you quickly the difference between producing biodiesel from different crops and producing it from algae. Corn, as example, we can produce 15 gallons of oil per acre per year. Oil palm, that is the best crop to produce biodiesel, about 600 gallons per year per unit area. But microalgae, that is now based on actual mass, they can produce 1,850 gallons of oil per acre per year. And estimations are indicating that should even, or that could even go further up to 15,000 gallons of oil per acre per year from microalgae. So there is no, in fact, comparison between producing oil from algae and producing oil from different crops. That is a similar study. Oil from corn, 172 liters per hectare, but from algae, which contains 30% fat, is close to 60,000 liters per hectare. Algae, which contains 70% fat, that is close to 137 liters per hectare.
Yes, what about the expenses? I mean, the comparative study is based on the quantitative
Yes.
over the area. What about the price?
Yeah. That is very important. A study which was done in 2005 has estimated the total cost, that is now inclusive of labor, inclusive of all facilities which is required to produce the biodiesel. They have estimated it to be $70 per barrel. That is the one produced from algae. Yeah. Currently it is $125 per barrel. Yeah. And I would say that producing biodiesel from algae would now cost less than $70 per barrel. But the study which has done that was in 2005, and their estimation was $70 per barrel. In addition to the previous advantages, I would like quickly to add that the ability of algae to accumulate oils or fats, they have a high ability to do that. Of course, not all the types of algae. A key point is to find the right algae species which can accumulate high amounts of fat. Biodiesel from algae is non-toxic. It contains no sulfur at all. It is highly biodegradable. Algae has a potential to grow on saline water and on harsh conditions as well. It requires less fertilizers. In fact, we can grow algae on wastewater, and that's what we are going to do in the following few months. If we grow our algae on wastewater, then in fact we are hitting two birds with one stone. On one hand, we will have the algae, and we don't have to spend money on nutrients for the algae medium. And the other thing is that we will also bioremediate our wastewater. That will purify our wastewater. Algae consumes carbon dioxide as they grow, and with that one I would like to show this slide quickly. Algae is a plant. It does photosynthesis. They absorb sunlight and they absorb carbon dioxide, and then they go under the photosynthesis process where oil and fat are produced, and they release oxygen to the atmosphere. And then we extract that oil, and then through a simple chemical reaction, we convert it into biodiesel. But I should say that algae will not reduce the level of the carbon dioxide in the atmosphere, but they will rather not contribute to its increase, because the amount of carbon dioxide which will be absorbed by algae during the photosynthesis will be offset by the carbon dioxide which will be released when we burn the biodiesel. So they will not reduce the level of carbon dioxide, but they will not enhance it, they will not increase that level, they will sustain it the way it is. That is a study which was done to compare the concentrations of harmful compounds and harmful gases in our normal diesel and in the biodiesel. So P100, that is here 100% biodiesel. So if we can look here, total unburned hydrocarbons, that is the concentration in the diesel, the petroleum oil. That is their concentration when we burn the biodiesel. That is the carbon monoxide, particulate matter, nitrous oxides. The nitrous oxides are also one of the green gases. So that is in petroleum diesel, that is here the biodiesel. Sulfates, there is no sulfates in biodiesel at all. Polyaromatic hydrocarbons, normal polyaromatic hydrocarbons, mutagenicity compounds, much less in biodiesel. Carbon dioxide, of course, is much less. And keep in mind that the amount of carbon dioxide produced here when burning the biodiesel would be somehow almost the amount of carbon dioxide which will be absorbed by the algae from the atmosphere during the photosynthesis process. So that in fact could be reduced to zero. In addition, algae can be used in the existing diesel engines. We don't have to modify any engines. We can use the biodiesel produced from algae with the current engines. We will use the same distributing filling stations. We don't have to have a specific filling stations. And as I said earlier, that a study which was done in 2005 has estimated the price inclusive of labor and equipment to be $70 per pair. In some countries currently, the biodiesel is cheaper than the diesel. So that is for 9 liters. I don't know what currency is that, but that is for 9 liters. That is also for 9 liters.
What would
98.9.
Sorry?
That's the price. 98.9
Yes.
and 111.9.
Well, that is for 1 liter?
That's for a gallon.
For a gallon? Yeah. I'm not sure, but what I'm sure of is that it is less for biodiesel.
About 20%.
Yeah. After extracting oil from algae, the biomass left is a high protein content, and it could be used as a livestock feed. In fact, producing biodiesel from algae could be the only way to produce enough automotive fuel in the future. We have started in the lab. We are growing algae on a small bench scale tanks. And the type of algae we have used is Filamentous algae. It is also known as pond scum. You find it anywhere on top of the water. It is a thread-like algae. And we were a bit unlucky because that was the algae which was abundant in our campus. But in fact, it has a very small fat content. But we decided to go ahead with it and see if we can enhance the fat content or not. And we also decided to go ahead and see if we can still produce biodiesel from the poor algae or not. We are still looking for the right species, but nevertheless, we tried to see if we can really produce the biodiesel or it is not feasible. And that is what we have done. We have harvested the algae every 10 days from the tank. We dried the algae. We have done a bench scale extraction using normal hexane and diethyl ether. And then after that, we extracted the biodiesel in addition to the normal hexane and the diethyl ether. We recovered our solvents again. So we recovered again the hexane and the diethyl ether. We can reuse them, and that is here the algae oil produced. And then we have done a trans-esterification to convert it from oil into biodiesel. And in the trans-esterification process, we mixed the algae oil with potassium hydroxide and methanol for 2 hours at 30 degrees Celsius. And then we have poured the mixture into separating funnel, so the biodiesel was separated on top of the liquid, and then we had glycerine at the bottom. We washed then the biodiesel with water, and then we dried it for 3 to 5 hours. That is air dry. And that is the simple, that is the trans-esterification reaction. That is here the oil produced from the algae. And when we reacted with methanol in existence of sodium hydroxide or potassium hydroxide, we produced the glycerol, and that is here the biodiesel. I won't go in detail. I'm sure that will not interest any of us here. We have tried to study the factors which can enhance the growth of the algae so that they produce more oil. And what we have found is that when we increase the concentration of the sodium silicate, when we increase the concentration of the trace metals, that is on the medium where the algae is feeding, and when we increase the concentration of the sodium EDTA, we have realized that the growth rate has increased by about 300%. And that is here just to show what we have shown in the previous table. That is the initial mass of the algae, the dark blue one, and that is the final mass of the algae after, I think that was 15 days. So with the sodium silicate, we had the highest growth rate, and when we increased also some trace metals, growth rates was very high, and that also goes to the sodium EDTA. Those are cheap chemicals, sodium EDTA, sodium silicate, and the trace metals. We have tried to study the effect of sunlight on the growth rate of algae, and we have realized that the more we expose the algae to sunlight, the more they grow. And we combined, so that was still here, we were exposing the algae 30 minutes every day to sunlight, 60 minutes, 90 minutes. So 90 minutes has given us the highest growth. And when we try to combine sunlight with carbon dioxide, we have realized that even enhances more the growth of the algae. So we are not looking only it in sunny places, but while it is in the sunny area, we provided extra or excess carbon dioxide. And that's what was happening. The one which was exposed to carbon dioxide and sunlight for 30 minutes, the growth rate was about 3 or 4%, and the one which exposed only to sunlight under the same experimental condition was only 175%. When we increased the duration to 60 minutes per day, the growth rate has also increased. When we increased it to 90 minutes per day, the growth rate has further increased. So that is the one here with the highest growth rate, that is 90 minutes per day sunlight and carbon dioxide. So to conclude, we have observed that the growth rate is directly proportional to the length of exposure of algae to sunlight and carbon dioxide, and we attribute that to the photosynthesis process, because they need carbon dioxide and sunlight for photosynthesis. So the more we expose them to sunlight and photosynthesis, the more they grow. And we have also realized that when we bring little algae or small amount of algae in large tanks, then they grow faster than if we bring if our initial concentration of algae is high. So algae which has given more space, they have grown faster than algae which was crowded at the beginning. We have also, as I indicated, found that adding excess trace metals and silicate solutions have enhanced the growth rate of the algae, and that is, in fact, could be attributed to the fact that the trace metals and the silicate solutions are reported to play a structural role in the chloroplast membrane, and they maintain the green color of the algae, and they break down pyrene into uric acid, and uric acid is an antioxidant, and it is a very important component of the genes. So that might be the reason. We have found that drying algae, after harvesting algae, we have found that drying it for 75 minutes at 80 degrees Celsius was the best drying time. Air drying is also possible. Sun drying is possible, but it will take a longer period of time. And we have found that the best solvent mixture to extract the biodiesel, to extract the oil from algae, is hexane and glycol ether 1:1 ratio. And after the transesterification, we have managed to convert the oil into biodiesel. 1912, Mr. Diesel said that the use of vegetable oil for engine fuels may seem insignificant today, but such oils may become, in course of time, as important as petroleum and coal tar products of the present time. I think we are very much approaching that. And it's not only the vegetable oil, but in fact, the algae oil. Countries are investing huge amounts of money currently in producing oil from algae, and I'm aware of some research groups in the States, especially the Army side. They are giving it too much interest. Also in Germany, and I know that there are some research groups also here in Egypt, Cairo University and Mansoura University. They have started doing something like that. And I would like that to be, in fact, in the energy map of Egypt. It might look insignificant again today, but it has a potential to replace the fossil oil in the future. Those are some references if anyone is interested. And at the end of the presentation, I would like to thank the University of Namibia for allowing me to come up all the way from Namibia to Egypt, and the Department of Chemistry and Biochemistry, my students, Martha Ambuto and Diana Gaz, and my colleague Celestine Lebron for the assistance during that research. And I would like to thank you for your attention, and I would be pleased to answer any questions.
Really, I'd like to ask what about the other sources of biodiesel? Again, if you would like, and just compare among these all these resources, especially from the economic
Point of view.
part.
Yes, yeah. From the economical point of view, I have no hesitation to say that it would be much cheaper to produce it from algae rather than producing it from other terrestrial crops. And one important aspect which we should keep it in mind is that when we produce biodiesel from algae, no one will blame us that we are causing starvation in Africa or elsewhere. China and Brazil are currently blamed for using corn